Hello everyone, and thank you for joining us for today's webinar. My name is Rami Eid. I am exploration geologist at Rashpetco. Rashpetco is a GV company with Shell, which operates in Egypt. Today we are presenting an overview of seismic data acquisition and processing. This talk will be presented by Dr. Hatem Farouq. Before we get started, if you have any questions during the presentation, please type them into the question box in your Zoom control panel. I will bring them up during the presentation, and we will also have a time for questions at the end. Now, we will turn the time over Dr. Hatem Farouq. Our presenter today is expert in oil and gas exploration and development, with more than 40 years of experience in oil and gas sector. Dr. Farouq has worked extensively in oil and gas industry in both technical and managerial positions with local and international companies such as GAPCO, British Petroleum, and currently with Perenco, North Sinai Petroleum Company, where he is exploration general manager and board member of FCGV. Dr. Hatem received MS and PhD degree in geology, petroleum geology, and geophysics. Dr. Farouq has taught industry-tailored and university courses as well as published and reviewed several research papers with local and international journals. In addition, he supervised and referred many PhD and MSc programs. He is a board member of Egyptian Geophysical Society, EGS, and active member of SEG and SPE. Thanks again, Dr. Hatem, for accepting our invitation, and you can start now.
Thank you, Rami. Hello, everyone. I wish you all are doing well and are safe. It's my pleasure to be with you today, actually for almost an hour, to cover a very important subject, but it will be like an overview. So we called it an overview of seismic data acquisition and processing. Seismic data is the most important geophysical method for hydrocarbon exploration and development. This is the contents of our talk today. I will start with a principle for the seismic reflection method. Then I will switch to the seismic data acquisition, in which we will cover the acquisition technique to understand how it works. Then the equipment overview will have some idea about the acquisition parameters. Then I will give you a clue about the land and marine acquisition in practice. After that, we will switch to the seismic data processing, which I will show you the contents when we reach half of the lecture. So we'll start with the principles. To have or to acquire seismic data or to apply the seismic method for hydrocarbon exploration, we have three main stages actually. It starts with seismic data acquisition, which contains also the planning for the acquisition. This is followed by a very critical and important stage, which is the seismic data processing. And this is followed finally by the seismic data interpretations, when we identify the subsurface geological features, structure and stratigraphic, and find out the best place for hydrocarbon accumulation. The seismic method, it's called a surface method. Why it is a surface method? Because we measure the seismic data or acquire the seismic data from the surface of the earth. So we can have, as you know, on the surface of the earth, we can acquire seismic data onshore, or what we call the land, or on marine, or what we call offshore. So we measure from the surface of the earth, whatever it is water, covered by water, or it is desert, or what in cities, whatever, to find out what's beneath the surface or what's in the underground that could be trapped hydrocarbons. So in seismic method, we acquire seismic data that will understand what's all about it now, And from this, we can know the details about the subsurface. The details, this means that the detailed geological information starts from the stratigraphy, the sequence of the rocks above each other, and their relationship, and the structure, and also to find out the best place for hydrocarbon accumulation. We can, from seismic data, reach to know the lithology of the reservoirs and the fluids within the reservoirs, either water, oil, or gas. Actually, we would like to have the hydrocarbon. So let's now understand the idea of the seismic method. It is very simple. I think all of us know the sound as I talk to you now. So how I talk and how you hear me. Okay, so, and also we are familiar with the echo. So if you have a source of sound energy, emits sound, for example, the sounds will travel until it finds an obstacle and it starts to echo back. This echo is the reflections. So sounds propagates everywhere, actually, in a sort of sphere until it reaches an obstacle, and then it starts to reflect back. Okay, this propagation of the sound energy is a wave. So the sound is propagated in a sort of a wave. These waves have like different amplitudes and different frequencies. And from these different amplitude and frequencies and travel times and velocities is what we measure from the reflection of seismic data. We can know the details of the subsurface, again, from boundaries to detailed lithology and fluid content. Okay, let's understand how these reflections appear on the seismic data. So suppose we have this succession of rocks that consists of 3 consecutive rock units, the green, the yellow, and the blue ones. Each rock unit of this has its own petrophysical properties, like the density and velocity. So each layer is characterized by its own density and velocity. And I mean by velocity here, the velocity of seismic wave propagation, the energy, how fast it propagates within the rock itself. Okay, when we multiply density by velocity, we came up with a value called the acoustic impedance. So each rock unit now is characterized by its own acoustic impedance, which is density and velocity. We have 3 layers now from geological or from rock units. This means that we have 2 interfaces. We have 2 interfaces between them. Okay, so if we have a sound propagate downward across the boundary of these 3 rock units, what will be happening? So if you have an incident energy, and it will find this interface. So part of the energy, of the seismic energy, will reflect back to the surface. How much, or what is the percentage of this incident energy will reflect back to the surface? It depends on what we call the reflection coefficient. The reflection coefficient is a simple relationship between the acoustic impedance of the upper layer and the lower layer. Okay, so now part of the energy will propagate and penetrate deeper. And it will again find another interface, and at this interface, it will reflect back according to the simple equation of the reflection coefficient. So the amount of energy reflects to the surface, okay, depends on the relationship between the acoustic impedances of the different successive rock units. How this will appear on the seismic section or seismic data, if we have like a reflection coefficient, if we have a positive reflection coefficient, it will be to the moment, represented by a peak on the seismic trace. And if we have a negative reflection coefficient, it will be represented as a trough on the seismic trace. So let's go further and understand what these traces will show us. If we have, what I mean, this sort of cartoon that represent a land acquisition, And if you see, you can see you have a successive rock units with different gray colors. So you have different boundaries, okay? And we have sort of structure. What structure means? Structure means how these rock layers look. So it looks curved a bit, that we call in geology, it is sort of fold. This is a sort of fold or anticlinal shape. How this will appear on the seismic section? This will appear on seismic section like this. So we have reflectors that represent the interfaces or the boundaries of the rocks. And we will have the shape, as you see. You see the shape here. It's curved again here, that we call this as anticlinal feature or folding. Okay, so let's now see an example of exact what I mean, succession of the rocks that is faulted, and we'll see how this looks on the seismic section. So this is a succession of rock. This is true section, and it is affected by faults, or what we call here normal faults, that is highlighted by these white arrows. How this will be appear? You see here the surface, and this is supposed that is observed. This is actually an outcrop, but I'd like to clarify how this will appear on the seismic section. So this will appear in the seismic section like this. We have set of reflections that reflect the boundaries between the rock units, and also we have some terminations, as you all see now. This will be interpreted as faults. Okay, so this is not only this, that we can see the boundary, or we can, or seismic data that what I mean, record the boundaries between the rock units, and from these boundaries we can know the stratigraphy and the structure, but also we can acquire or get some more parameter from the seismic, in which is that we can know the lithology of the rocks that we penetrated, or the seismic waves penetrated, and also the fluids. And we can take this from this graph, the distribution or the seismic section itself, so you can know the fluids, where is the hydrocarbon, where is oil, where is the gas, or the water. Okay, so seismic method actually is a treasure. It's a treasure, so you can see more details about the seismic, about the underground, which is the place where the hydrocarbon is generated and migrated and accumulated. So let's understand how we collect the seismic data in the field, how we record seismic data, or what is the acquisition technique. The acquisition technique that it is not known universally now, it's called the common midpoint method. So the main or most of the seismic reflection seismic methods that use the hydrocarbon exploration, it's use the technique of the common midpoint. Let's understand how this works. To acquire seismic data, as we will clarify later, suppose we have these two successive rock units in the subsurface with two different colors here. So how many boundary we have, or how many interface we have here? We have only one, because we have two layers only. And we acquire seismic from surface. Okay, and this will be the reflector in the subsurface. The reflector, because the energy will reflect back from it. So to acquire seismic data, we should have like source of energy, and we have receivers. And I'll give you an example of a spread consists of one source with 8 receivers, 4 at each side of the source, and this is what we call split spread, and we'll show you this in a minute. So we have source of energy, and we have receivers, and we'll know the details about them later. So the source of energy will emit the sound, and this sound will be propagate downwards until it gets this obstacle, the reflector, and return back to the surface, or reflect back to the surface from a point in the subsurface lie midway between the source and each receiver. So the subsurface midpoints here, it's called midpoints because it is the reflection points, and it locates at the mid distance between the source and each receiver. Okay, so if we have 8 receivers and 1 source, we will have 8 subsurface midpoints. Okay, when we acquire seismic data, we move up and start again doing the shot point several times, and we'll see what is the CMP mean now. So the output of this acquisition, or this only one shot, it will be like 8 traces on the seismic record. We call this gather is a shot gather, the gather of traces that is recorded when source number 1 emits the energy. So on, we will move up toward your right hand side. So the source location, so this is the midpoint. I will choose only this midpoint. I have 8 midpoints, okay, but I will choose only one of them to understand the technique of the common midpoint. So we'll see how many times this midpoint will be recorded. So we will move to shot point 2, okay, and we will have another record, okay, and the midpoint now start to called common midpoint. Why? Because it is the same midpoint that covered from the pale blue shot point here, this one, it's covered here twice, one with the red ray and one with the pale blue ray, and so on. We'll continue. I will show you 6 shots, so you see how we move. We will have number of source, number of shot gathers, and we will have the common midpoint will be covered several times. So how many times this midpoint, the one that start with from shot point 1, covered how many times? So it is the same midpoint, and if you remember, it is covered 4 times. One from the combination of source or shot point number 1 with its receiver number 8, the pale blue one. And then it covered from shot point 2 with the reddish ray and recorded at its receiver number 6. And also on the other side, we have it covered again 2 more times with a combination of shot point 4 and its receiver number 3, and the shot point number 5 with its receiver number 1. So it is covered 4 times. When we gather the traces of this midpoint, we call that we sort the data into the CMP gather. We'll end up with 4 traces. Each trace comes from one of these combination. Because of that, you have different colors here. While it is the same subsurface point, okay, you see that it is recorded at different times because the scale, this vertical scale, is 2-way time, and the time increases downward. So this came at earlier times than this one, and this one came later. Okay, so all of these traces are of the same subsurface point. So it should be all aligned. So we use processing. We apply a correction called normal without correction. We will cover again in the processing. So what this criteria, which is the delay in time for the same subsurface point with distance, is called normal move out. And the processing step that we applied, it's called normal move out correction. Okay, then we flatten these reflectors, because we will apply another processing step that we were going to talk about, which is called stacking. And with stacking, we'll sum all of these 4 traces into one trace, and you see here how the amplitude of the data get bigger. Okay, so this is why we use the common midpoint, is to cover the subsurface point more than once, just to be clear on the final seismic section. One more word I'd like you to know, which is now we recorded the reflections from the same subsurface point 4 times. This is what we call the fold of coverage in seismic. Okay, so the fold of coverage in seismic is the number of times that you reflect the energy from the same subsurface point, and in this case it is 4. So the CMP gather will contain the number of traces that is equivalent to the fold. Okay, so let's continue. Let's see how we record this data. So what is the equipment that we use or we call it in other words, the acquisition system. So the acquisition system is composed of the seismic sources and the recording. So three main components for the system that we used for the seismic acquisition. Let's go through one by one. So starting with the seismic sources. What is the seismic source? The seismic source is a transducer that produce sound energy, because as we start, if you remember my second slide, it was about the echo of the sound. So the energy that we use for seismic method is the sound energy. Okay, so we need a device that emits sound energy. Okay, so the seismic sources is a transducer that can convert any type of energy, whatever it's a potential energy, it's a chemical energy, into sound energy. Okay, and this sound will propagate as we just discussed. So the first one and very famous source of energy is the dynamite. You know the dynamite with its bang. It has a very loud sound. It's a very good seismic source. It's an excellent actual seismic source because it contains a lot of frequencies and it penetrates deeper in the ears, and it can cover actually or can be used on land, the onshore, or in the marine or the offshore. It needs some precautions in handling, but it is a very good seismic source. The second one, which is a very simple one, is the weight drop. So if you use a hammer like this slide here, it will generate sound, okay? And this sound will propagate downward. Okay, so we have also another manufacturers type of weight dropping sources. So you can have a crane, for example, that raise about 3 tons of concrete, and you leave it, and then this will flow in the ears, and you will have the sound energy and this type. So dynamite is used for a land and marine environment, but weight drop will be on the land environment, on land acquisition. So the seismic source, as we understand, could be as simple as dynamite and weight drop, or more sophisticated, like what we see now. What we see now is another type of manufactured sources, that like the vibro-size, the air gun, and the water gun. The vibro-size are, as you see, is a truck that contains electromechanical system, and in this source we can use a signal, or we can emit a signal that takes a period of time. We call this the sweep, with a change in the frequency. So we can have an upsweep that start with low frequency and end up with high frequency, or vice versa. This is, of course, used in the land acquisition, and it is very famous and very successful because it covers long areas in short time, and it is simple to use and program to have our sweep. The air gun is a marine source, so we use the air gun in water-covered areas. The air gun simply has a chamber that we fill with a very pressurized air, and this is stored behind the seismic vessel or the boat that doing the acquisition, and it at the short point location, this air will be suddenly released underwater and form a balloon, and the water to reach to the equilibrium, it will contract this balloon and it will do a sound. So this is the source, because our source is sound energy. We need to have sound energy. The other one is the water gun. It is nearly the same idea, but it is not generate a bubble of air, it generates a cavity, the water gun. So water gun and air gun are marine sources. Vibro-size is a land sources. Weight drop is land source. Dynamite is both, can use both. And again, the seismic source is any device or equipment that can produce sound. Then we'll go to the detectors. So how we detect, how we're gonna detect the reflections that come from the interfaces between rock units or from the boundaries of the rocks. Actually, we have two main receivers. So let's first know what is the function of the seismic detector. Any seismic detector, the function of any seismic detector is to convert the reflected seismic waves, which will be in the form of earth motion, vibration, if you acquire on the land, or pressure pulses if we acquire on marine data. So to convert this reflected energy into electricity. So the main function of the seismic detectors is to change the seismic reflections, which is the sound wave energy, into electricity. Okay, I will understand more now why it is electricity. So when we acquire on land, we use the geophone. And the geophone is simply a magnet that hangs in a coil. Okay, and when the vibration came from the underground, the magnet will vibrate in the coil, generating an electromagnetic field, which is transferred into electric energy. The marine seismic detector is called the hydrophones. Hydrophones, we have a piezoelectric cell. This piezoelectric mineral that used for in the hydrophone converts the pressure pulses into electricity. Why it is pressure pulses in the marine? Because you know we have the water, the column of water. You will miss the vibration that comes from the sea bottom, but when the vibration came and touches the water, it converts from mechanical energy into pressure pulses. So this one, the hydrophone, is used for water-covered area, and it is sensitive for pressure pulses, which is reflect the reflected energy. The other type, and it's very important, it is a combination between the geophone and hydrophone, and we call it the gimbal geophone hydrophone, and this is used in one of the seismic methods that we will cover later, which is ocean bottom cable or ocean bottom node seismic acquisition. So how the energy, we said that these devices convert the seismic reflection into electricity. How this electrical signal went to the recorder or transferred to the recorder, we use the cables. So we have land cables and we have marine cables. So it is an electrical cables, okay, but of durable, what I mean, very hard cables. And the cable for the marine, it's called the streamer. So the marine cable is called the streamer, and we call it a submergent buoyant cable because it is usually when you acquire the seismic data, this streamer or this cable was tied behind the vessel and at depths of about 8 to 10 meters below the sea surface. Okay, and it contains a hydrophone inside it. Okay, so how we record the seismic? So now we know how we acquire, we know the technique, it's the CMP, and then we know that we use some sources to generate sound energy and use receivers to detect the reflected seismic energy and convert it into electrical signal, and the cable transfer this electrical signal to the recording. How I record the seismic data? Okay, at the old days, the seismic data was recorded analog. So we have a sheet of paper, and you start from a scale of 0, okay, and you start to have your vibration or the Earth's vibration, okay. But later, after that, the scientists find out the digital recording, and in digital recording, we took this vibration or the seismic reflection and sample it, take a reading of the sample every constant milliseconds or every constant time, and convert that into numbers, okay? And we use a binary system and type this digitally on a magnetic field table. So the data is reformatted from analog, what I mean from the shape of the waves into numbers. It is like the graph. If you have an x-axis and y-axis, and you get some readings from your wave, okay? But it is written to the storage media. It is most properly a tape that I will show you the shape of the tape now. But because the advantage of the digital recording, it is written by the computer language, and the processing are using computer programs, and so we can, and routines, so we can process the data very easily and simply. And also acquire a huge number of data, so the analog recording is not anymore used for seismic exploration, but the current one that is used is the digital recording. So how we type that? Are we put some numbers in the binary system, some numbers, any numbers? How we put this together? So we need to have a format or a standard format for this. So what I mean, issues a standard format is this SEG, the Society of Exploration Geophysics. It is published the standard format. So if we have field format means the data that recorded in the acquisition in the field. We have SEG, or we called it in the industry SIG. So we have a SIG A, and it is updated by SIG B, SIG C, and the current field format is the SIG D. Okay, but if we process the data a bit, the format will be the SIG Y. This is how the data stored. The format means how the data is stored. Okay, but if you have some velocity data, we will start with the navigation data, because navigation is very important. We have to know from the field the XY location for each receiver and each source, and the elevation and so on. So this is stored on storage media with a format called UCOA format. And if we have a velocity, we'll have the Shell V5 or the SO V2. This is how the data looks or written on the tapes. Okay, and this is digits. Okay, this is digital. We will see when we go through the processing what we're gonna do. Okay, so when we acquire the seismic data, now I have the system. What are the parameterization? What's important when I design my acquisition? We have 5 things that I'd like you to concentrate on, which is the sample rate, the offset range, the receiver spacing, the recording length, and signal to noise ratio. For the sample rate, you remember, this is the sample rate is the period of time that we take the reading, or when we convert from analog to digital. This is the sample rate. Okay, it has relation with the frequency, and if we take it wrong, we'll have some sort what we call temporal aliasing. And then we'll have the offset range and receiver spacing and recording length. This is to understand that we have 2 geometries. The one on your right-hand side, it's called the split spread. This is the one that I showed you when we were talking about the technique. And this one is a single-ended, or the off-end we used mainly in the marine configuration. And to understand these parameters, so the distance between the source and the first receiver is called the near offset. The distance between the source and the furthest receiver is called the far offset. And the distance between 2 successive receivers is called the group interval. Okay, the offset and the recording length. Recording length means that how many seconds I will record the data. Because seismic data is recorded in time, that is 2-way time. Okay, not in depth actually, so it is in time. So the offset and the recording length has big relation with the target depth. So my target depth is shallow or deep, or I have multi reservoirs or multi targets. The group interval is very important for to see the reflector, the interface as a whole, and if it is dipping, what I mean. So suppose if you have a mirror and you have a light on the mirror, when you move the mirror, the reflection will go in different directions. and you need to collect all the reflections to know the shape and the depth of your reflector. So this is related to the group interval. Wrong group interval take us to a very bad problem with seismic, which is called a spatial aliasing. In the signal to noise ratio, we will talk about this more in the processing very soon. So let's see acquisition in practice. So you hear a lot about 2D and 3D seismic. So let's see what is the difference between 2D and 3D seismic in both marine and land acquisition. So for the 2D, we acquired across profiles, which is called seismic lines. And these seismic lines, as you see, it's a few number of lines that are intersected to each other. In the strike of the structure, the surface structure, and the other one perpendicular to it, and which we call the 2D. How we know the strike and the depth? We can use another geophysical tools, or we can use the surface geology. Because of that, we have geological trips to know generally about the structure of the area. So and the sources in the same line. This is the 2D. But in the 3D, we acquire lines. I mean here the receiver lines very close to each other, parallel to each other. Okay, so either in the marine. So we have 2D and 3D acquisition, and we see that the difference are in the design of the lines themselves. We have intersected lines. This will be 2D, few number of seismic sections. So what we gain from both, from 2D and 3D. So from 2D, we'll have nearly the same number of profiles that we acquire in the field. We will have vertical sections as you see here. So same number of vertical sections. So if you acquire 5 lines in the field, you will end up with 5 of these vertical sections. This is a vertical geological cross section, but in time, in two-way time. This axis is a two-way time. But on the 3D, we'll end up with a cube of data. This cube of data, you can cut it in different directions. So you can have like vertical sections, like the 2D, and also you can have some horizontal slices that, and most of the applications of the advanced seismic techniques is based on the 3D. So there are other types of acquisition. When I have if you remember at the beginning, I said that we can know the lithology and the fluid. So to know the lithology and the fluid, we need to have the shear wave to be recorded with us, not the P wave only. And as you know, in water, does not propagate. Because of that, if we are in a marine area, in the sea or ocean or whatever, we use the ocean bottom cables or the ocean bottom node. In the ocean bottom cables, this cable laid out on the sea floor, and it has the gumball geophase. So, with the progress in the industry, instead of using the cables, we use nodes. The nodes is boxes that contains both hydrophone and geophone. So geophone on land, on the sea floor, can detect the shear waves. Okay. Also, if we have obstacles like salt domes, any type of rocks that prevent the seismic energy to be propagated deeper, we can use other type of acquisition, what we call the multi-azimuth acquisition or the wide azimuth acquisition. Actually, the narrow azimuth acquisition, what we call NAS, this is the normal one that I talk about, but the multi-azimuth, for the same point, we acquire the data in different directions, and the wide azimuth, we have the source boat away from the receiver boats, so we can cover lateral, more or much larger lateral area. With this, I conclude the overview of the seismic acquisition, and will go quickly with the seismic data processing. So seismic data processing is the second stage in the seismic method. As I mentioned before, and it's a very important stage, very critical, because you can end up from seismic processing with fake subsurface geology or with true subsurface geology. Okay, because of that, it needs more understanding about the science. To understand more about the seismic data processing, we'll give you some definitions and principles, and then I will understand what signals and what are noises. Then we'll talk about the processing flow, where we say that pre-stack, post-stack, or whatever. And then I'll give you some real data examples to understand the application. So for definition or principles, seismic data can be represented in different domains. Let's understand what means by different domains. If you have water, the water can be liquid as we drink it, or it can be changed to solid state as ice, or to gaseous state as gas. This matter state, the data of the seismic data, which is the sound energy or the reflection, can be represented or plotted in different states, but we call the domains because states is of the matter. So the first plot in your left-hand side that I have the arrow on it now, this is called the time domain. What I mean by time domain is that I represent the reflections at each trace, and the vertical section here, the vertical axis here is a two-way travel time. So this is what we call time domain. But with sort of analysis, it's called Fourier analysis, we can convert this data into the frequency domain. And in the frequency domain, I can see this data like graphs, as you see here, between frequency and amplitude, or I can plot it in an FK filter, an FK plot that we are going to talk about. Or we can go to another domain, which is called tau B. This is the seismic data that you see here. So this time data is like it's here, and it's the same data, but it is represented in different domains. Why I represent the data in different domains? Because to separate the noise from the signal, and we'll understand now what's noise and signal, I can separate them in one domain better than the other domain. There is another name of domain that is the geysers. So we can have the seismic geyser. If you remember in the acquisition, when we acquire the data, I said that this is the source geyser or the shot geyser. And then when we collect the traces for the CMP, we said that this is the CMP geyser. So data in seismic can be gathered in different geysers. What I mean, the traces, what I mean, to be in sample in different geysers. And this is what we call the pre-stack. So when we apply processing on this geyser, type of geysers or domain, this is called the pre-stack. And then when apply the stack, and I end up with the stack section and apply any processes, this will be a post-stack process. Okay, so let's go further to understand about the flow. What's signal and what's noise? Signal and noise, both are sound energy, both are reflections. Okay, but the signal is the wanted reflections. Signal is wanted reflection, which reflect the real subsurface geology, reflect the reflections that come from the boundary of the rock, different rock units, while noise is any other type of sound energy that is recorded while acquisition. Okay. So if we have this record, actually this is one record with a mirror image from each itself. So if you take a look here, please imagine what are the signal and what are the noises. So if you remember in the acquisition part, we see that the reflector zone comes beside each other, nearly flat. This is the reflection from the subsurface geology, but any other directions are the noises, unwanted energy. So what we see here is like this. So this is what I highlighted in red are the major reflections, which represent the geology, but we have some refractions here at the shallow part. We have these linear noises. This one came from what we call an air wave, and this is come from the ground roll. Ground roll is traveling of the sound from the receiver on a superficial boundary to from the source to the receiver. So the signal is a wanted energy that reflects geology. Noises are unwanted energy that reflects any other thing. So if we, to understand more, if we see these are two records, okay, two field records. Can you now imagine where are the noise and where the signal? So just to save time, you see what's highlighted on red? These are noises, it's unwanted energy. After processing, I remove all of these noises. You see the difference? This is before processing, this is after processing. This is before processing, and this is after processing. Okay, so after processing, where are the reflections? You said that the signal will be appear. So in seismic processing, we said that seismic processing is responsible for increasing the signal to noise ratio. So what I mean, to diminish the noises as much as we can, and we have as a signal, we have the data full of signal, which is the geology again. So now, if I go back here, this is before processing, and this is after processing, and you can notice what we removed from the data. What we removed are the noises, but now where are the reflections? Where are the signals? So in this one, we improve signal to noise ratio, but where are the signal? The signal is here. You see these packages? This is hyperbolic shape reflectors or nearly flat reflections. These are from the ears. So these are field records. Let's see that on final stack section. So this is a stack section. This is a final product stack section. It's a final product is a processing in which we can interpret a structure and stratigraphy. We can talk geology only in the stack section. So what you see here, this is a low signal to noise ratio seismic section. Where are the signal? It is nearly the flat events that you can see hardly, because this is before good processing. This is the raw data, but after processing, it will look like this. You see where is the improvement? Improvement is here. What you see now is the reflectors of the subsurface geology. So in the processed data, you increase the signal to noise ratio. These were the principles, and to understand the signal and noise, now we'll go to the processing flow. So seismic data processing is formed of many steps, and these steps are sorted on a flow. Okay, a 2D processing is different than 3D processing. Land data processing is different than marine data processing. Actually, there are some main steps that is common between both or all, but it is different from one to one. So let's see some steps, the name of some steps, and after that we will see a real example to understand them. So we start, for example, with loading the data. From where this data came, these are the field data, the data that I collected after acquisition. Okay, then I will start with a step called demultiplexing, then geometry, and the geometry is a step where I upload the processing software with all the navigation measurements from the field. You remember what are the navigation? It is the XY for each source and each receiver, the elevation for each source and each receiver. Then we'll have a step called editing and muting. This is followed by amplitude correction, frequency filter, deconvolution, CMB sorting, velocity analysis, normal VOD correction, staking, migration, and post-processing. In the industry, we group every group of steps and give them a name. Like this one, we call the pre-processing stages. When we apply other steps before stacking, this is called pre-stack processing. And any process after stacking, it's called the post-stack. Okay. How we apply this? We do tests. We do apply tests to the data. So we have our input data, and then we test how to what I mean increase signal and diminish the noises. So we end up with several with tests with several parameters. We compare this with the input data as I showed you before, and then if, for example, parameter number 2 was gave me the best result, so I will apply the step with parameter 2, and so on. So we'll test the parameters for the next step. Step is the different names that I showed you, and I will show you again now. And then I will apply the best parameter for that, and then I output my data. So this is to remind you with the flows that I just showed in the previous slide, but a different way. I'd like to add here that within the pre-stack processing, I can apply some processes in the short domain or the CMP domain. You remember the domains when I talk about that in the principles? Okay, so again, here is pre-stack processing. This is post-stack processing with different names of steps. Now, let's see how the effect of these processing steps on the seismic data itself. Okay, so we'll start with the first processing step, which is called the demultiplexing. And simply speaking, the demultiplexing, you remember I told you that in the acquisition, we record the data in digital format. Okay, in demultiplexing, we took this digital format data and reformat it to the software, the processing software format. So any processing software has a format to see the data and to start to differentiate between signal and noise and try to increase signal and eliminate noise. I have to see the data visually in front of me. So the data comes from the field, as I told you, recorded on magnetic tapes with any shape from the one you see here. And you remember that it was recorded digitally, sort of numbers. When I apply demultiplexing, it will convert it into the software format, and it will be a sort of plotting. What domain is this? This is a time domain, if you remember. This is a time domain data. So now I see my field data or field records. So this is the first step. We have now the data, as you see plotted in the time domain. Then I will go to, I have to check my data. Okay, or are all the traces of my data contains right reflections, or I have some bad recording data. Bad recording data could come from, I will leave you take a look here and see if you have some traces that have different appearance than the neighbors or the other traces. So we have, you see these ones, the three traces, we call these bad traces because they don't have the same reflections as the traces surrounding them. This may be for different reasons. One of them is that the detector itself, either the hydrophone or the geophone, was bad, unfunctioning. Okay, so the trace editing step, in the trace editing step, what we do is we multiply these traces or the amplitude of these traces by 0, and we end up with this record. So it is the same record, but after applying the editing, the trace editing step on it, we sort of remove the bad traces from this. So trace editing can edit only one trace, can edit sort of traces, can edit a complete record, can also convert the peak into trough and the trough into peak. This is what we call polarity. So it can reverse the polarity of the data. Why it is polarity? Because you remember the reflection coefficient. Okay, when we have positive reflection coefficient, what I'm gonna plot it on seismic will be peak or trough. This is the what I mean polarity. So editing can change the polarity. So this is as simple as this, as one of the steps. We can do this manually, or we can do it automatically. We call it automatic edit. I can identify to the software, processing software, that the bad traces has an amplitude of thresholds, so and so, and we can remove. And going to the trace muting after that, when we record the data like this, I have here six records. Okay, from 6 sources. You remember at the very beginning when we talk about the technique. Okay, so where are the reflections? The reflections are those ones that have hyperbolic shape, but near the surface or at earlier time, we record some unwanted energy, like the refraction. If you remember when I showed you signal and noise, the refraction here, and I have some bad data as the far offsets. So the unwanted data, how I can remove it? We just remove it by editing. But if I use editing here, I will remove all the data. So we put a line, identify a line that, and told the software that all the data above this line is unwanted data. These are noises. Please mute it off. Please cancel this data. So I can clean my data like what you see here. So this is a trace muting. One of the very important corrections to seismic data is what we call the static corrections. What is static corrections? You know that if you acquire seismic data onshore, on a land area in the desert and whatever, you have different topography. So you have different elevations. So you will have in some part of the lines, you will have the source and receivers at elevation, for example, 10 meters above sea level. And in others, you will find it 5 meters below sea levels. And in others, you will be at the mean sea levels. Seismic data is recorded in time. So if the starting and ending point, which is the surface, because at the very beginning, I told you that this is a surface geophysical method. So we measure from the surface. So we put the receiver and the source at the surface, and we measure the reflection in time. So if the surface is not flat, you will get the reflection at later and aerial times comparing to the, the topography. Static correction is very huge subject, but I will show you the examples to understand. So if you see here, I have 2 examples, one colored, your left-hand side, and I have these black arrows, showed you that the reflectors are terminated, and broken. You see the broken, how the is broken here. And this is again here, if you see this reflector, it is broken elsewhere. And broken in geology means false. So if you have terminations and you have the reflector is broken like this, so you have false. So if I interpret this data, I will put many false actually, but this is not true because this is before applying the static correction step. But see, after the static correction step, where are the terminations? It is very smooth and it reflects a domal shape or anticlinal shape. And here it is flat reflector without any termination or error. So you see how processing is very critical, is very important. This is what we call the stack section. This is the final step of the seismic processing, which is here on the stack section where I can interpret my geology. So if I output this from the processing, I will end up with a subsurface full of faults. So I can find like a place for a trap, and I would drill a well, but it is wrong. So this is a fake subsurface reflections. But when I use a correct processing, then I will correct for the topography. But for static correction, I mentioned the topography only, but also there is the superficial rock layer, which we call the weathering layer. You know that the rocks are weathered at the surface because of the air or the water or whatever. And this weathering layer is characterized by very low slow velocity for the seismic waves. So it prevents the seismic energy to go propagate downward, and we correct for that. So static correction is a set of corrections for the change in elevation, for the weathered layer thickness, the weathered layer velocity, and also to refer the data to a constant datum. Again, to have the start, and the reflection at the same dot. Going after that to the amplitude, and the amplitude, how strong is the reflector appear on my seismic data, whatever pre-stack or post-stack. And with amplitude, I will show you 3 examples. One of them we call the correction, which is the spherical diversion. I'll show you the second one is the AGC, automatic gain control, and I will show you after that the balancing of the data. So working with amplitude at the beginning to correct the amplitude. Suppose the source of energy, when it emits its energy, and at the very beginning I told you that energy propagates in a sphere. So the sound travels. So to travel distance, the sphere should be get bigger. What I mean, so the radius of the sphere will get longer and longer. Okay, does the energy will be the same, or the energy will be decay away from the source of the energy? Will be decay away from the source. Yes, it is decay actually. So this is how the data looks after the demultiplexing. Where is the data? I didn't see any reflection. I don't see any reflections here. No, the amplitude is this blue, is this black colors here, but it is concentrated near the source because the surface is here. Here is deeper, or later time, which is deeper, corresponding to deep. So if I know how the radius, how much is the radius or whatever, or the decay curve, how percentage the decay happens with the distance, I compensate for that. And this is the same record. This one is this one, but this is after I applied the gain recovery or the spherical diversion correction as much. You start to see the reflectors here. So now the amplitude, as you know, is the reflection, how the peak appear or the trough appear. You can see the reflection. So this is a matter of correction. I have to apply it. When I say correction, correction means that it is a mandatory step. But I can, do more than that artificially. I was using another gain correction, which is called the automatic gain control. In automatic gain control, you see this is a record now. And if you concentrate here, you will see that the reflection end up here. So because the source is supposed to be here, and this is a shallow depth and earlier time, and this is deeper depth and later time. You see that you lose the reflections here. Okay, but when I apply the AGC, you start to see the corrections everywhere. Okay, but this is your maximum. No, I can have another one. This is your maximum. No, I can see the data like this. So what are the differences here? The difference is in the parameter. You remember when I told you that I do tests and I choose the best of them. So the parameter here called the window. So if I increase the window, I will see the data like this. So each one of you will choose the ones that show him the reflectors in a better appearance. Okay, so this is the AGC. Another one, but using different parameters, which are called the balancing. You see here, if you start here, all the black here is the amplitude that is concentrated near the source and in the shallow part, but going deeper or later time, because this is you can't see anything, but you can balance this amplitude and see like this. In this one, this is what we call linear noise. This is linear noise, and these are the reflectors. Going further, so let's talk about frequency filter. I showed you the domains before, and there was a scientist called Fourier. Right? Fourier said that I can change the domain of the seismic data from time domain using the forward Fourier transform into the frequency domain. And when I go to the frequency domain, you can plot the data in amplitude spectrum, frequency spectrum, or phase spectrum. In this case, in this domain, you can differentiate the signal from the noise better than the time domain. Okay, so I can cut what if I identify where are the noise, I can cut it like this. So I can have the low only frequency, or I can have only the high frequency. Where the low and the high frequency, this axis is the frequency. Frequency increases direction. Okay, and this is the amplitude. So frequency increases direction, and the upward is the amplitude increase. So I can cut whatever from this data what I want, and then bus filter, for example, notch filter, and return back to the time domain. So this record show the data before the frequency filter. You see this linear noises here. This is called the ground roll. And you see how it masks the reflectors. So after the filter, this is gone, and you get the reflector now. Some of you will see, oh, you have faint amplitude here because you remove this. How can I correct for that? How can I correct for that? How can I correct for that? You just take the amplitude recovery. So I can use AGC, I can use balance to reconstruct the amplitude here, and it will be appear whatever as you want. You can change the window, just see the AGC now. But this is how the filter. So I went to the frequency domain here to separate noises from signal. Now we'll go to the deconvolution. And in deconvolution actually the straightforward meaning is to remove the effect of the seismic wave from the reflection. We call the seismic wavelet as a unit. Okay, but actually this is what is not happened. We reshape the wavelet, or we reshape the structure to appear much better, much continuous. Okay, so deconvolution has different types of deconvolution and can be applied in different domains. So I will give you two examples only. So from the effect of the deconvolution. The first that it is deconvolution, it's sharp the reflectors to appear very sharp, and this is what we call the spiking deconvolution. We can remove the reverberation of the water or the short period multiples when we use the predictive deconvolution. There are other types of deconvolution. So let's see before and after just to get the sense of the difference. Please take a look and see what are the differences. This is in your left-hand side is before applying the deconvolution. This is after applying the deconvolution. And this is a stack section that you can do geology and the structure now. So just to save time, if you take a look on this package of reflectors, so how sharp it appears here after deconvolution, how continuous are these? Okay, you see this package. So you see the difference, how sharp it is here, how you can see it continuous and sharp. Okay, where are these noises? The hashing. You see this hashing? It went gone away. Okay, so this is the deconvolution. Going to another way of filter, which is the frequency filter. In frequency filter, you see, as you see, this is a time domain data. You have these flat events are the primaries or the signal, and these linear noises, these linear events are the noises. We can go to the frequency domain again, but in this case, we will plot them in a graph that have the frequency and the wave number. One axis is the wave number and the other axis is the frequency. So in the linear noise, this is what we call the FK filter. FK filter with frequency wave number. So the linear noise here appear as dipping event on this plot. So any dipping event here is the noises, but the one that has zero dip, which I have this rectangle about it, is the data itself. So I will mute all of the dipping event and return back to see how you remove this linear noise. This is the FK filter, very important one. Then we'll go to the multiple attenuation. Multiples means that it is the repetition of the reflector. It's like the echo. Very dangerous actually. So if you see this is a marine stack section. Marine means that this is water and this is the sea floor, and you see that this is repeated several times here. This is water is repeated several times. So this is repeated and it is not found there, and also it masks some of the primary reflectors. So this is after multiple attenuation. You see that most of these are gone away and some of the real reflector start to appear. Different types and whatever. So normal VAD correction, I will go through this very quick because we talk about it. The only thing that I need to add in normal VAD correction is how we calculate this delta T to have this hyperbolic flatten like this. We use the velocity. So this is called the velocity analysis. With velocity analysis, we see the the best velocity that calculates the delta t to have this hyperbolic shape reflector to be flattened, because I will gather all of this into one trace, and this gathering is called the stacking, and the stacking is here. You can talk about geology, you have folding, for example, in this one, but we can talk about any geology here, pre-stack. The stack is the final and important one. Finally, and the last thing that we are going to talk about is the seismic data migration. And seismic data migration is a critical and very important steps, because we count it as a correction actually for the data. And correction means that it's a mandatory. So seismic data migration is responsible for moving the CMP reflection to its correct subsurface location. Okay, can be moved in vertically in time or laterally. So let's see some examples. Why we need the migration and see its correction? Because the assumption of the seismic method is that the reflector are flat. But if the reflector is not flat, we have a lot of structure. What will appear on seismic section? Take a look on this section. You have some flat reflectors, but you see those? This is we call bow tie. From where this bow tie comes from? Because this came from a syncline. So this is before migration, but after migration, I will have the synclines like you see here. Okay. Also, if I have a lot of diffractions like this means that I have termination. This is before migration. After migration, all the diffraction gone, and I can put faults here. This is if I have an anticline. Okay, and this is what happened after the migration. So, for example, if I have a salt dome like this, you see how the reflectors move with the salt dome, but you cannot locate the wall of the salt dome exactly, because this is unmigrated or before migration. After migration, you can see the salt dome very clearly here. So one main factor to have a correct migration is the velocity. So what I have here is a seismic section with a velocity model spliced on it. The velocity model here is each color is a velocity value. So you see how the salts are found here. So we have different velocities than the other. You see how detailed is the velocity. The color means the velocity here. So, and how it matches with the structure. More and more, this is a very difficult or very complicated structure. You see how detailed is the velocity model. We use here what we call full wave inversion, and you see how the seismic data looks like. With this, I conclude actually very big subjects in almost an hour. I'd like to thank you for your time and your listening. This is my contacts, so you can reach me at any of these contacts. And also for, I have an Arabic tongue, so if anyone wants to talk to me, you can contact me or approach me at any of these contacts. Thank you.
Okay, thanks, Dr. Hatem, for your informative presentation. Actually, we learned a lot from it. And we will go ahead and take some time for questions now. Question number one says, what is the difference between CDB and the CMB?
Very good question. So CMB is a common midpoint and CDB is a common depth point. So if the subsurface reflector is flat, CMB is equal to the CDB. Okay, but if the subsurface reflector is dipping, now the CMB is not the CDB. Okay, so the midpoint is the point that you receive the reflections from it, and it is in the midway between the source and the receiver. So this is the main difference. What I mean, give you the right CDB is the migration that we use. When I talk about migration, I said that it moves the CMP subsurface point into their right position in the subsurface. So migration makes the CMP equals to CD.
Okay, Doctor, thanks for that. Another question, it says, how dynamite can be used offshore without affecting negatively the environment?
Thank you. It affects the environment, actually. It affects the environment. So it is prohibited. I said that you can use it in the marine. We were using this before, but actually it affects the environment. It kills fish and other creatures in the sea. So it is, some countries, the dynamite is totally prohibited. But it is used mainly on land, okay? Uh, in the area, in the soft land, actually, if you have farms or whatever, so you can use dynamite there. So it is prohibited actually in the market.
Okay, thanks, doctor. There is another question. What is the difference in idea between sonic logging and seismic exploration? Is it the same idea?
Uh, Nearly so. The sonic is a borehole measurement. Okay, so you have a sound, a source of sound that emits the sound into the formation, and you count whatever when you count the difference between two receivers. Okay, so you don't the sound in this case, in the sonic case, does not travel from the surface all the way down. But in the seismic data, you have the source and receivers on the surface. So the energy goes one way, all the way down from the surface to the reflector and the subsurface, and return back same way up to the surface. So when we build, for example, the synthetic seismogram, when we build a seismic trace from sonic log and density log, we have to calibrate the sonic velocity to the seismic velocity, because that we should have a velocity log, which is like the seismic.
Okay, thanks, doctor. The last question says how to differentiate between actual and fake faults in the processing phase.
Would you please repeat it again?
How to differentiate between actual and fake faults in processing phase.
Okay. Number one, you have to make sure that you apply the static corrections. Okay, so you should know if it is a land that you compensate for the difference in elevation or compensate for the difference of the weathering layer velocity, because this is what will bring you the reflections at a fake time that you could put a fault or whatever. Okay, so first thing you have to apply static corrections. Number two, when you apply processing, you have to have a judge, a QC, and the very important QC if you have a geologic information, and the best source of geological information is the well information. So if the area that you apply processing and have some geological information like from the well or whatever, you have to tie your data with the well data before and after each step of the process.
Okay, thanks, doctor. It looks like we have covered some questions. And now, doctor, is there anything else you wanted to cover before wrap up?
No, thank you. And if you have any question, I will be happy to answer at any time.
Okay, great. Thank you, doctor. Thanks for your time. Thanks, everyone. We appreciate you are being here and hope to see you in our next lectures. Thanks a lot, Dr. Hatem.
Thank you very much, Rami, and thank you for all that. Thank you.
Okay, thanks, doctor.